let us begin this party. So what is this? This is technically week 11. So this, I think, I'm pretty almost positive that this is actually lecture number 31. Does it really matter? I guess not. But it's nice to pretend we remember what's happening, even if we don't. So, bring up my notes from last class to see where we ended. We ended. Oh, that's right. We did a triple integral. Oh, that's right. So last class we ended with that fiasco. We were working on, so we were showing you one of the 6 different ways. Whoops. So last class ended with an important, I guess that's Ann. Of an important integral that was triple. Important example of a triple integral. So I would encourage that, and maybe you did, hopefully. So what was this, by the way? This was number 2 on homework 10. I always forget, does the period go outside or whatever? Doesn't matter. So hopefully you guys write it the other 5 ways. That's good practice on some important concepts. So one of the things that it's good for is it is good practice on changing the order of integration, which turns out to be one of the more useful things from a practical purpose. All right, so if you look at the rest of this homework, what we end up doing is we ask you to do some more integrals. We tell you sometimes to use different coordinate systems, so it's probably important that we do that right now before we do these applications. Does anybody have a question or a comment before we do that? All right, so I said this earlier, I think twice. I said it on Friday, and I definitely said it last Wednesday. The triple integrals are just a very natural generalization of double integrals. And if you think about it, thanks to Fubini's theorem, a double integral is just a generalization of a regular integral, for the most part. Now, we can get into technicalities if you wanted to, but that's not for this course. In this course, as in most things that we study in engineering and science, the mathematics is very natural. It's not created or designed to be for counterexamples. So the integrations that we want you guys to do in here are very natural generalizations of what we've already been doing. And so it turns out, too, that there's a very natural generalization to polar coordinates. One of the things that humans realized a heck of a long time ago is that things that were circular or spherical or curved, or the more general term is curvilinear, anything that moves not in straight lines but in curves can be better described using, oftentimes, different coordinates than x's and y's. That's the whole point of polar coordinates. So what we want to do today is we introduce 2 useful coordinate systems. in R3. So I want to preface this by repeating myself, something I've said over and over again. Depending on what our ultimate goal is, we might want to choose different coordinate systems. You know, if we're mapping a city like New York, we would use a grid. And you can think of the grid of New York or Manhattan as sort of X and Y coordinates. Everything's up and down or left and right. But as you guys know, if you've ever seen a globe or you've even thought about traveling on, you know, the surface of the Earth, the best coordinate system for a sphere is not necessarily the XY coordinate system. In fact, we use longitude and latitude, which is a completely different concept than the traditional XY coordinate system. In different areas of physics and engineering, we use other types of coordinate systems. So the coordinate system that you're most familiar with, the X and Y, the reason that that is the one we study so much is because it's the easiest to teach. That doesn't always mean it's the most useful. And the XY coordinate system is also the one we do the most with, is because it's easiest for the simplest things, namely curves in the plane. But when you no longer are interested in just simple geometric figures, but more complicated ones, we often have to, you know, extend our knowledge, or not our knowledge, but extend the types of coordinates that we use. So that's where we're at with what are called curved linear coordinates. So the first one is what's called cylindrical. So this takes advantage of things that are curved in one plane, but not in the other. And you could imagine a cylinder. So what's a very simple cylinder of, oh boy, that's a terrible cylinder. Maybe I'll do some straight lines and make it a little easier. So how might we construct this cylinder? We might say it looks like this. So the question is, how might we describe this? And the fancy word for this is analytically. That is, can we give you equations and the equations describe this surface? Just like the equation y equals mx plus b describes a line, or the equation y equals x squared describes a parabola. How do we describe a cylinder? So here's how we can proceed. So one way is to note that a horizontal slice gives a circle. So what do I mean by that? That is, intersect the cylinder with a plane that is parallel to the XY axis, or the XY plane, I guess. And so if you do this, the intersection you get is a circle. I guess I should learn how to spell. So maybe we'll draw a picture of that to help illustrate. Does anybody have a question right now? At least I'll try to draw one. Probably the best place for you to experiment with this is GeoGebra. Once again, we'll try to draw this. So here is our cylinder, or if you want, my rock star can. What I want to do is I want to intersect this with some plane. So let's get another color. Let's say green. So let's try to give it some perspective. And so what is the intersection of these things going to be? Well, the intersection of these things is going to be some So again, if you take, imagine I take a pop can and I slice it horizontally, or I intersect it with a plane. What's left? You know, another way to think about this, if you must, is just take your cylinder and turn it sideways. What does it look like? It looks like a circle. Now, what this suggests is it suggests that there is a very natural coordinate system or a way of describing this. So, does anybody have a question before we talk about that? Now, I've said this before, and I don't know if you think about it. When I say something is suggestive, if I say this suggests, we have this, I don't mean that it's obvious to you in 3 seconds. What I'm saying is if you spend some time pondering about it, maybe 20 minutes, maybe a day, maybe a couple weeks, you have to think about it. Now, not every minute, but you know. Then you realize, oh, I see why this makes sense now. So when I say it suggests something, I'm not saying that it was suggest to you instantly. Because if you put this in perspective, excuse me, human beings have been looking at cylinders since the beginning of written history. It took them thousands of years to figure out how to put algebra and geometry in the same thing. So it was not obvious to the human mind. But once you take the time to learn this stuff, it becomes clear, oh, I see why we're doing this. So what does this suggest? Well, it suggests the following. So the first thing that we're going to say it suggests that we can describe a cylinder as. So it depends on what we want to do, but let's imagine we want to describe this thing. What are these points? Well, it's X, Y, Z, such that what characteristics do these points have? Well, we know that X squared plus Y squared has to equal some radius squared, because all the points in the XY plane, if you think about it, are in a circle. And then what does Z range from? Well, Z can range from some fixed point to another. But if I imagine that cylinder extends in all directions, I can say Z goes between, whoops, I might say that Z ranges between negative infinity or infinity, or if you'd like, you don't have to make it go on forever. You could say something like x squared plus y squared equals r squared. And Z ranges between some values. Maybe the smallest one is E and the largest one is some number F. Depending on whether this cylinder goes forever and ever and ever vertically or if it stopped. So the first thing you need to understand is that a cylinder's equations, or the set of all points that make up a cylinder, can be given by these sort of equations. Does anybody have a question? So right now you're saying, what's E and F? Well, we are now in Calc 3. You have to understand that if I write a letter down and I don't tell you what it is, then by assumption, it just represents an arbitrary number. Maybe my cylinder has a top and a bottom. Well, F would be its height, its top, and E would be the number that represents how far down it goes. If I have negative infinity to infinity, the idea is that that cylinder is infinite. It continues vertically and negative forever and ever and ever. So context is the key for all of this. So let's do an example real quick to help see what I mean more specifically. Does anybody have a question? Okay, so let's try to draw something in a much more sophisticated way. I'll put my z-axis here, my x, my y. So we know what this is: x, y, and z. Now let's try to draw something that's a little illustrative to what the above notation means. So let me get a new mark. I don't know if I want the purple. So what I'm going to do is I'm going to try to label some stuff so maybe it's a little clearer. So here's the top of my cylinder. So if I put some points here, maybe I'll label this 4, that 4, and then maybe this is height, say 10. So what is this cylinder here? This is the set of all x, y, z, excuse me, such that x squared plus y squared equals 2, because 2 squared would be 4. And then z ranges between 0 and 10. Now, does anybody have a question about this description? Now, here's something else. If we want the solid, if we want all points inside, what do we have? Well, you'd have X, Y, Z such that. Now it would not just be the circle, it would be the disk that includes all the points inside of 2. Does anybody have a question? Okay, so here's another thing. And I'm going to write this in red because I want you to never forget this the remainder of your math and if you take any physics or engineering courses forever and ever and ever. So the x squared plus y squared screams circle and thus sines and cosines. That's what you should be thinking all the time. All right, so when you have that, so we have the following definition. What are our cylindrical coordinates? Well, we know from polar coordinates we have x equals r cosine theta, y equals r sine theta, and z equals z. And these are equivalent to, let's write them in terms of the new variables. What is r? R squared is sine squared. Well, okay, let me not get ahead of myself. I don't want to scare you. What is r squared? R squared is just x squared plus y squared. You know that theta is the arctan of y over x, and then z is just z. So, by the way, what I've written on the right-hand side is the same thing we wrote a few classes ago for polar coordinates. It's just now we have a third variable, and it doesn't change in this particular instance. So let's draw a picture of that while you write this down. I'm going to take my time and try to draw this for you. Actually, let me shrink this. You hear that? We got excitement upstairs. So let me try to draw my little coordinate system again. And let's think about, we might have a point. Say we have some point in space here. I guess I'll do it this way. So what I want to do is I want to think about this point. If I go way up on top of a building and look down at this point, what is its reflection into the XY axis? So don't forget that this is our Y axis, this is our X. And so there's a projection of this point. And where does that projection go? Well, it comes out here a bit. And you can also measure it from the x-axis, or from the origin in the x-axis. So if we label what all these things mean, and this is just elementary geometry, you don't get so worked up. So again, if this is the point, what's this distance from here to here? This is z. The distance from here to here is, well, we have a triangle here. So if this is a triangle, this is the distance. This is x, which is r cosine theta. This is y, which is r sine of theta. And of course, this angle in there is theta. So again, a good way to think about this is whatever you're sitting in right now, look at one of the corners of the room and think about that corner as the x, y, z coordinate system, and then put your fist in the air and think about measuring your fist. If you had a light source above your fist, it would cast a shadow onto the floor. That shadow would be this, what we call the projection. It would be the point right there in the plane. I'm pointing at it, you guys can't see, but what I mean is this, I'll label it in green. This point in the plane, this would be the shadow cast if I brought a light source straight above this point. Does anybody have a question, comment? Okay, so if no one has a question, let's think about why this is useful. So when integrating, this often is useful. So a quote unquote big theorem tells us how. Now, I am not going to write down the details of this scary theorem. The details, or it's just not worth our time. We're better off doing examples. So the key point, the key idea is we change variables from x, y, z to r theta z. And most importantly, what is dv? dv ends up equaling r dr d theta dz. That is the key point. So instead of writing down this scary theorem, look, you can look it up in the book. They're big, scary theorems. Let's do an example. Right? I mean, think of this. When we were in Calculus 1, did I ever state the U substitution theorem? No. I said, here's how we do it. You know, we never stated some big fancy theorem about how it works. All we said is it works and you have to trust us. If you want to know why it works, you go study theory classes, but that's not the point of this class. So the best way for us to understand how this works is to just do things. Is everybody okay with that? I don't think don't see why you wouldn't be. Okay. Do, 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 do. We good? No questions? Any questions? All right, so let's look at the homework. Whoa, I hit the wrong button. I didn't want to do that. So I'm going to do something similar to the homework. I don't want to do the same exact one, but here's what we're going to do. So let's suppose we have the following integral. -5 to 5, 0 to 16 minus x squared, integral from 0 to 2 of 1 over 1 plus x squared plus y squared. So I'm giving you one that's very similar, and then we have dz dy dx. What does this integral equal? So as you've seen with the last two homeworks, I can give you an integral where the bounds are already there, and I can ask you to integrate, or I can give you an integral where I don't give you bounds, I just describe the domain, and then you have to figure out the bounds. So I'm trying to give you a fair amount of each type of example. So the example we finished class with last time, I told you what the D was, and then we figured out one set of bounds, and we asked you to figure out the other bounds. Now I'm giving you bounds of the domain, and we have to figure out what the heck this domain looks like. And it turns out that if we describe this domain in cylindrical coordinates, that the integral becomes much easier. Would anybody like to ask a question before we begin? Now, it's not 100% necessary all the time to draw the domain, but I think you should get in the habit of that. So what I'm going to do is I'm going to draw the domain, or at least sketch D. So what is D? We could see what's happening. We can see what's really happening already. So let's remind us that this is not given. So this is the solution. What is D? Well, I can read directly off. Why does this do this? Stop it. I can read directly off my bounds where everybody goes. So what I'm going to do is I'm going to look first at DZ. So if I come up here and I just get a different color, I'm going to put an arrow above DZ. And then I'm going to get a different color and put an arrow above DY. And then I'm going to get a different color and put an arrow above DX. So then I'm going to put the corresponding colors here. Where does X range? Well, the first thing we notice is X is the outer guy. X is the last guy. So he corresponds to the outer integral bounds. So we know right away that X goes between 5 and 5. That's what we know. Now, this pink tells us what y does. What is y? Well, y goes from 0 to 16 minus x squared. I'm going to write that a little cleaner. And then lastly, what does z go from? Well, z, which is in this green, z goes from 0 to 2. So I'm trying to use these colors to make it a little more of a learning assistance in learning for you. Does anybody have a question about how I got these things? I mean, again, I'm reading them directly off the bounds. The only subtlety is, do you got them in the correct order? Z is the inter guy, so that's why z goes from 0 to 2. Then dy is the middle, so y is the middle bounds. And then lastly, x is on the outside. Now, I can sketch this thing. And by the way, let me do something, because I want to make this a little easier. I should have, can you guys do me a favor? Is this going to kill you if we switch? Take this 25, make it a little easier on us. Take that 16 and erase it, and let's make it 25. I hate to do that, but it's just going to make what we do is slightly easier. Because what is 25? 25 is the square of 5. It's just going to make this problem slightly easier. I should have thought of that. So maybe put an X through that, or just mark a note that O'Grady's changing it. I apologize about that. That's just going to make what we do more, not as ugly next. Okay, so let's sketch this thing. So if I go and I get my XY coordinate system, or my XYZ, I guess. Okay, so what do we know about this creature? Well, we know this creature, where x goes from -5 to 5. We know where y goes, and then we know where z goes. Hi, Ricky. You saying you gonna come play? We got a crumb snatcher down here. So once again, I can draw this cylinder, and I'm going to try to do my best to draw it to scale. So the cylinder is going to look like this. Now, where does y range? Well, y ranges between 0 and some equation. So if you look at this line right here, this is just a curve. Y equals the square root of 25 minus x squared. Let me make that a little cleaner. So if you need some more assistance, this is the point. Let me use black, make it a little more clear. What is this point right here? Well, this is the point 0, 5, 0. This point right here would be 0, 5, well, how far up does z go? It goes to 2. Clearly, this is not to scale. What is this point? Well, this is on my x-axis, so this point is 5, 0, 0. So this is, in fact, a cylinder. Again, not the scale. She's fine, Aim. She's playing with her Legos. Now, notice that we said y ranges from 0 to this curve. So are we interested in this whole cylinder? And the answer to this is no. So you have to be very careful. Note we said y. Where does y range? Well, y ranges between 0 and this curve. So I'm only interested in the portion of this cylinder that's in the positive y portion. So what you need to understand, and this is maybe not so clear, is the following. Since 0 is less than y is less than this, we're only interested in half of the cylinder. So I'm only interested in this, the portion where y is positive. That's it. So if I come and draw this down, I'm only interested in this portion of it. So it's hard to draw this, but I hope it's starting to make sense. Okay, so this means a couple things. I'm going to let you guys catch up. If you have any questions, please let me know. So if we go back a second, a couple things that need to be thought about. Notice that if you tried to integrate this thing with z first, that wouldn't be an issue. But then if you wanted to integrate with y and x, it's going to be much more difficult. In fact, you guys might not even know the algebraic tricks to do that. So what I want you to understand is that integrand, the one divided by that stuff, that would be nearly impossible, if not extreme, or very difficult, if not impossible, to do in x, y, and z. And the reason is you have two variables in the denominator. That poses a problem. Now, fortunately, we know that cylindrical coordinates will take x and y, two guys, and replace it with just one letter, which is r. So, okay. Anybody have a comment or a question? So, let's use cylindrical coordinates. And again, you might say, well, how would I know this? Well, anytime you see an x squared and a y squared, it is literally like an alarm should go off. If you see x squared plus y squared in any integral ever, you should immediately think polar or cylindrical, depending on whether it's 2 dimensions or 3 dimensions. Now, the only question is what are our bounds going to be? Well, we already have our z is easy. So what are they going to be? Well, they're going to be, as we already know, x equals r cosine theta, y equals r sine of theta. Now, where do r and theta range? Well, we know that r is no bigger than 5, and we know it's no smaller than 0. Now, what's tricky here is where does theta range? theta is clearly never going to be smaller than 0, but we're not going all the way to 2 pi. We're going to pi. So this is a subtlety that most people would miss up. We're not going all the way around to create a full circle because I'm only taking half of this cylinder. I'm taking my Rockstar can and I'm taking a knife and vertically slicing it. So I'm taking half my cylinder. So you can already see that there's a ton happening in these problems. First thing you got to do is figure out the geometry of everything. We haven't even done any calculus. I mean, really, we haven't. We've literally done nothing but do what we call analytic geometry. We have a shape, and we're trying to describe it using algebra. That's all we're doing. But this is perhaps the most important part because you can't answer anything about the geometric properties unless you have this sort of thing happening. By the way, you might say to myself, you might say, well, what is this even useful for? Okay, well, imagine, suppose we have a metal rod. You might say, what is this integral? What realistic things can this integral represent? Well, imagine I have a metal rod, but maybe it's not a full metal, maybe it's hemispherical instead of cylindrical. I slice it in half. Maybe this function inside that we're integrating, that could tell us the temperature distribution of the rod. So you might imagine a rod that has a certain thickness. Well, if I'm heating it, it's not going to have the same temperature on the boundaries as it does inside, right? That makes sense. I mean, you wouldn't imagine, at least not at first. I mean, you guys, I think you're quite aware of this. If you had something on a hot stove and then you took a knife and put the knife on it, is your hand going to burn immediately? Well, probably not. It's going to take time for the heat to transfer. Imagine an airplane. You guys are well aware that the temperature on the surface of an airplane is going to be different outside than it is inside when you're flying at 25,000 feet in the air. Do we understand that? So imagine an object that's being heated or cold. And this isn't the only example. There's lots of examples. But imagine maybe this integral represents the average temperature of a steel beam or something like that. So that's one way to think about a triple integral. I don't know if that makes any sense to you, but perhaps, you know. Okay, so how do we integrate this then? Well, let's set it up. Here's how I would set it up. The first thing I'm going to do is I'm going to write down 3 integral signs. And then I'm going to write down my function. But I can't write it down with x squared and y squared because it's not x squared and y squared. We know what x squared plus y squared is. It's r squared. So I'm going to write like this. And then we know what my dv is. My dv is r dr d theta dz. So notice I didn't write any bounds yet. This is the O'Grady strategy. The O'Grady strategy, and let me remind you this whole creature here. This whole creature is dv. That's what this is. The r dr d theta dz. Ricky, what are you doing? What are you doing? Yeah, that's funny. Okay. So, excuse me. Now what I'm going to do is I'm going to work from the inside out. I'm going to go over here and I'm going to say, okay, what are my bounds? So I know the first letter that I'm integrating is r. What does r range from? Well, on the previous page, we saw r goes from 0 radius to 5. What's next? That's theta. Where does theta range? Theta goes from 0 to pi. And then lastly, z. Well, z goes from 0 to 2. Fun times, huh? Now, here's the beauty of cylindrical coordinates. Look at this. Do you see a theta or a z anywhere? No, we don't. So look what we can do. We can kill those guys right away. If I integrate, right away, I know where does z integrate out? Well, if the integral of z, if there's no number there, or excuse me, no letter, it just becomes z from 0 to 2. So this gives me 2. And then when I integrate theta, I get pi. And so the only thing that's left then is the integral of r. So this is 1 over 1 plus r squared times r dr. So I want you to think about that. That is one of the beauties of using different coordinate systems, is it basically makes certain things automatic. So here's what I'm doing here. So this, if you need some sort of guidance of what I did, I'll show you. So here's what you should note. The integral from 0 to 2 of dz is just z evaluated from 0 to 2, which is 2. And then the integral from 0 to pi of d theta is just theta from 0 to pi, which is just pi. See, these are just automatic. Now, it might not be automatic for you. You might have to ponder this for a few seconds, but that's, again, one of the hidden gems of this. Does anybody have a question about that? Okay, so how do we do this integral now? Well, this one, you might think it's an arctan. It's not, because you have an r squared downstairs and an r upstairs. So the correct way to integrate this guy is to do a u substitution. So what is this creature? Well, this becomes 2 pi. Now, what's this integral? This integral is going to be 1 over u du. And then I'm going to have times a 1/2. And I'll explain why in a second. And what is your new bounds? Well, your new bounds are going to be 1. And then your upper bound is going to be, well, let's think about this. So let me write this down over here. So let's put this on the side. Let's choose another color. Let's choose green. So what is my substitution? My substitution is u equals 1 plus r squared. So my du is 2r dr. So another way of writing that is that 1/2 du is equal to r dr. So that's how I get this du here. Now your bounds. What are the bounds when I switch to u? Well, the denominator is going to be 1 if I replace r with 0, I get 1. And if I replace r with 5, I'm going to get 26. So if you have a question about that, holler. Anybody have a question about this? I mean, again, no one's pretending this is easy. And at this point, you're also probably burned out because all the math we make you take is Calc 1 and 2 and 3. It's such a mean thing. They don't show you any other cool math. They just bang your head against calculus for a year and a half, right? Sorry, you guys will get new other classes in the summer and the fall. Different type of math. Does anybody have a question about this? Okay, so what does this become? Well, this becomes, the 2's cancel. So this is pi. And then when you integrate this, it's the log of u from 1 to 26, which simplifies to nothing more than pi times the log of 26. Why does the 1 disappear? Well, because log of 1 is 0. What a time to be alive. We're having so much fun. Whose head's ready to explode? Don't shoot the messenger. Just, enjoy the message. I'm cold here in my basement, by the way. It was nice and warm yesterday. Suns were out, guns were out. Okay, who has a question? It's an interesting thing that this integral has two wild numbers in it, a pi and a natural log. It's funny how pi shows up in all the weirdest places. Okay, does anybody have a question? Okay, all right, so let's blow your mind with the next topic. So our next coordinate system is called spherical. So let's write this down. Now we're not going to go through drawing pictures again. Hopefully you get the idea. What are spherical coordinates? Well, we're going to use spheres. So instead of using a cylinder to sort of describe where a point's located, we're going to use a sphere to describe where it's located. This is extremely useful in many applications. If any of you took chemistry and even studied the simplest things like the hydrogen atom, you'll understand that we imagine an electron orbiting the nucleus. And we talk about these orbits, these spherical orbits. That's just one example where this crap shows up all the time. Okay, so what are the spherical coordinates? Well, we're going to have the following. Instead of having r cosine theta, we introduce a new letter called rho. And then we introduce two angles, one called phi and the other called theta. And this looks scary, but honestly, if you do it a few times, you'll never forget it. In fact, I've never forgotten it, and I've been doing this. Well, I guess it's not fair. I've been doing this for a long time. So what is the system? Basically, you have this beautiful thing. And the key thing to take from it is rho squared. We're not going to. The key thing to take is we're not using r here. We're using a different Greek letter. We're using rho. And the key observation is that it takes your three coordinates, x, y, and z, and removes it down so that instead of three variables, you have one. And then if you want to find theta and phi, they require ugly trig. So it's not important. The important thing is this top equation. All right, so here's what's important. And you need to understand this following thing. This phi can be no bigger than pi. And theta, as we had with polar coordinates, can be no larger than 2 pi. So we're going to draw a picture of this in a second. Does anybody have a question? Comment? Now these formulas look very like out of nowhere. They're not. We're going to draw a picture in a second to help illustrate where they come from. But what I really want to draw your attention to is this equation, because the purpose of what makes polar coordinates so useful And what makes cylindrical coordinates so useful, and what now makes spherical coordinates so useful, is in this pink box on the right-hand side. We are taking 3 variables and reducing them to 1. That's the goal. And so that often makes many integrations very, very, very easy compared to what they normally would be using x's and y's. Does anybody have a question? All right, so let's draw a picture real quick to see sort of what's really happening behind the scenes. At least I'm going to try to draw a picture. So once again, we have our x, y, and z coordinate system. And so let's once again imagine we have a point in space. So let's put it right here, for example. And what we're saying is if you project it down, maybe I'll try to use a different color here. If I take this and I project down, where is it living above the plane? Suppose it's some point right here in the XY axis. So I'll draw this point. So what is this point? This is the point X, Y, Z, but Z is 0. So let me be very clear about this. If I'm in the XY plane, then my Z value is 0. What is this point? This is the point X, Y, Z. Now, we want to also call this something. We want to call it, instead of X, Y, Z, we want rho, phi, and theta. So literally, we could teach you spherical coordinates in high school. We can teach you this in trig. It's not complicated. There's just no reason to introduce at that point because you don't see when you'd ever need it. But now you know. Okay, so what do we have? Well, let's draw some more lines. Let's try to illustrate what's happening here. If I imagine the distance from here to here, and then I can also imagine this distance. So right now you see I have a triangle in space. So how do you imagine this? Again, look at a corner of your room, put your fist up. Imagine that there's a line from your fist to the origin, and then there's a line from your fist to the ground. That creates a triangle. That's what you're seeing here. You sort of see this. This is a triangle. So maybe I can sort of try to shade this in. And don't forget that this is, in fact, this right here is a right angle. So what are our angles here? Well, this guy, we already know this is theta. That's how we've been measuring things. What is this angle? Well, this angle from here to here is phi. So if I have this triangle, this is just elementary trigonometry sort of planted into a much more advanced world. So all you have to do is you use things like similar triangles, and you use basic trig identities. And if you use basic trig identities, what you see is the following. So what is the distance from this point to this point? Well, that's just Z. But we can write this. Again, you have these angles floating around everywhere. So using similar triangles, this green dotted line is parallel to the, excuse me, by the way, this is wrong. Oh my Lord, she's firing me. This is not the y-axis, that's the z-axis. So notice that the green line is parallel to the z-axis. And so you learned in high school geometry that any line that intersects parallel lines, you have opposite interior angles are congruent. So when you learned that as a child, that means this angle right here also phi. The length of the hypotenuse is rho. Right? That's the length of the hypotenuse. Now, I can't do this for you. What you have to do if you truly want to understand where they come from, and I'm not saying you have to do that. When I was in Calc 3, I don't think I had any clue where these rhos and phis. I just memorized the formula. In retrospect, that was a bad idea. I should have taken more time to try to figure out where they come from. But it's not that difficult if you just think about where this triangle lives. And again, the best advice I can give you is I actually did this one semester. If we were in a classroom right now, this is what I would do. I would literally, swear to God, I would put my fist in the air, and then directly underneath it, I would mark the ground. I would take a sheet of paper. And then what I would do is I would measure the distance from each wall to that piece on the ground. And what you would realize is where all these numbers come into play. So, for example, the distance, and I'll use a different color. If I look at, say, this point right here, which is corresponding to my x coordinate, the distance from here to here, using just elementary trigonometry, is, what is this distance? It's x equals rho sine phi cos, excuse me, not cos, this one's sine. I'm losing my mind. What is this distance? It's not x. The distance from here to here is your y. I'm sorry. Oh boy, something went. That's my mouse. So it's sine phi sine theta. And then similarly, you can measure the distance from here to here. So I don't want to make light of it that it's super easy, because it's not super easy. Hold on, I just shattered my mouse. Oh boy. I think my mouse is broken. Oh boy. We got technical difficulties here, friends. Give me 1 second. My mouse fell, and now I can't even use my... Okay, so how do I say this in a way that's not going to scare you, but encourage you to maybe try to learn? It's the following. So using basic trig and geometry of the pink triangle, what you can do is you can derive the spherical coordinates. So I'm not going to spend the time doing it. You can do it on your own. That's probably a better learning experience. You should try it. I did one of them for you. And what I mean by the spherical coordinates, I mean what I wrote down on the previous page. Okay, so what do we need to take from this right now? What's the big point? Before I give you that, does anybody want to ask a question or a comment? Anybody want to get in a fist fight? Go, yeah, so you're crazy. You know? My kids are upstairs. They're funny. They're fighting right now. Okay, so once again, we have a big theorem. we won't state. What's the key idea? What is dV now? This is the key idea. So before you had dA, when polar, it was RD, RD theta. So the key point is, what does the big theorem tell us? Well, it basically tells us the following things. dV equals, hold tight, rho squared sine of phi d rho d phi d theta when we switch coordinates. So this is what you need to keep in mind. This is the big useful part of this. And it's worth keeping the following in mind. So I'm going to write it down. Note, polar, cylindrical, spherical, when you use these coordinates, all this is just a generalization of U sub from Calc 1. And so here's the thing that you don't want to Google. Well, you could, but your head might explode. They are all cases, and we'll talk about this briefly, of what's called a change of variable theorem. So basically what we're telling you is when you learned U sub back in Calc 1, you were changing variables. You were going from X to U or from T to U or whatever. And essentially what that meant geometrically is that you were going from an XY coordinate system to another coordinate system. That's what it meant. If you go back and think about that and draw pictures, you're like, oh, holy hell, yeah. And now we're telling you that we can do the same in 2 and 3 dimensions. And the most useful coordinate systems are polar, cylindrical, and spherical. This is not easy to learn. Of course, you guys know that. Does anybody have a question before we leave? Does anybody have a question about any of these slides? By the way, I'll post these slides again, and I'll post the lecture. I don't know if you guys are looking at it. Anthony's running a marathon in his house. Very good. I like the pictures. We don't see Emily. We don't see Mr. William. I don't know where Peter is today. He must have joined the wrong thing. So he just left. Anthony must have just lost it. He pulled the plug. Okay. So what's next then? What's next is, so the following. We will briefly discuss that idea in applications next time. So if you guys don't have any questions, I say go in peace and try to study these homework problems. You might actually ask, you're going to say, well, how do I do problems like center of mass? Well, first off, there is Google to help you. Second off, these are elementary things from physics. If you know the density of an object, what's density? It's mass per unit volume, right? That's density. Problem is, as you can imagine, most things in the real world do not have constant density. And so integration is key to understanding that. If you can't do 6 and 7, that's fine. We'll show you how to do those next time, but they're things to think about. Does anybody have a question? All right. Well, look, if you have questions, if you want to meet, I'll be happy to do virtual office hours. Otherwise, I would encourage you to email me or do whatever. Does anybody else have questions before I? All right. Well, then I will stop recording.